We will now solve problem 1 given in the 2016 fall exam. So here we have different types of questions. First we have an equation, an inequality, an equation involving logarithm, a couple of derivatives, and an integral. So let's dive straight into the equation. What we basically would like to do is to find x as a function of something with y, or y equals an expression of x. And we can do that using whatever equation we want. For example, if we would like to find an expression for x from the first equation here, we will have something like this. So we divide by 5 on both sides. These are not difficult, but more difficult than if we simply use the y we have here. So I'll show you why. Here we simply get 11 minus 4x. So we have y as a function of x. And then we can insert that y, this expression here, into the first equation. And that's simpler than taking the expression here for x into the second. Simply because these numbers are easy to work with than these, but you do what you want. It will give you the same results. So we substitute the expression for y into the first equation. So we have 5x minus 4y equals minus 2. And we substitute 4. Instead of y, we now write 11 minus 4x equals minus 2. We multiply minus 4 with whatever is in the parentheses, so minus 4 times 11, which is minus 44. And we have minus 4 times minus 4x, we get plus 16x. And that will give us 5x plus 16x equals minus 2, and we move the minus 44, or we could say that we add 44 on both sides. You can use that notation if you want. Vertical line and then something that will say that you do that on both sides. So minus 44 plus 44 becomes 0. And now we have 21 x's and we have 42. Then we do this again. We multiply with 1 over 21, which will give us x equals to 2. And then we insert x equal to 2 into expression for y, namely this one. Y equals 11 minus 4x, then becomes 11 minus 4 times 2, which is 3. And then we check our solution. We're actually asked here to test the solution, but it is a good idea to do it anyway, because if you've done something wrong, you will discover it. So in the first equation, we had 5x minus 4y. So we get 5 times 2 minus 4 times 3, which is 10 minus 12. It's minus 2. and that was what we had here. Then we had 4x plus y in the second equation. 4 times 2 plus 3 becomes 8 plus 3, which is 11, which is also what we were supposed to get. So this is okay. So then we have our solution. In B, we have an inequality, and that's basically an equation. We just need to make sure, because if we multiply with something negative or we divide by something negative, we should turn this inequality sign around. But we could plus and minus just like we do with equations. So x over 2 plus 1, let's equal to 4 plus 2x. So the first thing we would like to do is to gather everything with x's on the same side. So in order to do that, we need to subtract 2 x's to get the x to the other side. And this one thing here, we also need to get to the other side, so we need to subtract 1. So we do that on both sides. So we have x divided by 2 minus 2x less equal to 4 minus 1. So we're not supposed to turn this one around because we haven't multiplied or derived by any negative numbers. Okay, now we have x half minus 2. So we have a half minus 2, half minus 4 divided by 2, which will be minus 3 half. Just to make sure. But you could also simply just write that like this. Okay, so now we have something with x equals a number. I now need to get rid of this minus 3 over 2. So I multiply with minus 2 over 3. If I do that, my 3 over 2 multiplied with 2 over 3, I will cancel all the 3's and the minus, and I will end up with 1. That's on the left hand side. I now multiply with something negative. So now I need to turn this around. And then I have 3 times minus 2 over 3. So I'll get x equals to or larger than minus 2. And that was it. I could check, simply put x equals to minus 2 and see if I get the same on both sides. I could also put something larger than minus 2, for example 0. If I do that, this term will cancel on this one, and 1 is less than 4, which is good. Just to see if I'm doing the right thing. Okay, now we have a logarithm to 2x. So ln, that's a natural logarithm. And with e as a base. If we use log, we have 10 as base. So now we have an e. And I would like to have an expression for x, and it's trapped inside this logarithm thing. So in order to get that out of the trap, I put e on both sides. Okay. E, ln, that kind of cancel each other. So I get 2x's equal to e to the third. So I get x equals to e third divided by 2, which is, if you put it into a calculator, 10.0 approximately. And we test our results. So I want ln 2x to become 3. I could put simply 2 times 10, which would be my approximate value, and I will get 3. Or I could put the exact values. 2 will cancel this out, and we will have ln e3, which will be 3. So whatever method we use, we are okay. Okay, now I need to find the first derivative of an expression here. I see that I have something with x multiplied with something else with x. So I think I'll use the product rule. I will put u equals to x squared and v equal to sinus 2x. And I'll find the derivative of those. You could also use this notation if you want. It means the same. So x squared becomes 2x because the derivative of xn would be nxn minus 1. And here n equals 2. dv dx, or with the other notation. Okay, here we need to find the derivative of sine, which is cosine. And we have 2x trapped inside the cosine. So we need to multiply with the derivative of 2x, which is 2. So we get 2 cosine 2x, according to the chain rule. Okay, so we have f of x equals to u times v, since we put x squared equal u and sinus 2x equals v. So our derivative of x will become u v plus u v. Okay. So the derivative of u is 2x and v equals sinus of 2x plus u, which is x squared, times v, which is 2 cosine of 2x. Two x sinus 2x plus 2x squared cosine 2x. This is the pretty order. So you have the number first, then the x's, and then the sine and cosine stuff. So that would be our answer. In E, we have a sine of something with x. So here we need to use the chain rule. So we need to put x squared plus 2 equal to our kernel. So let's put that into a u. And the derivative of u would then become 2x here plus 0. And if we have f of u, that would be sinus u. So the derivative of that would become cosine. So f derivative of x, and again you can write it like this. I see that I mix these notations. Will be first the f du times the u dx. So it would be cosine of u first times 2x. I put that in front, and we can exchange the u for x squared plus 2. When I did this now, I did it very stepwise. I explained how the chain rule is used, and here I explained how I use my product rule. If you're familiar with this, you could make a shortcut, simply write product rule, and use the rule directly. So it becomes 2x, the first derivative of the first times the other, plus the other times, no, the first times the derivative of the other. And then clean up, and you're okay. And down here, you could also go directly, simply use, write that you use the chain rule, and then go directly to your answer, like this. And then you need to use the derivative of the kernel, and you get 2x cosine of x squared plus 2. That would be the shortcut, and it's okay. Okay, here we need to find the indefinite integral. So you see that you have something here which makes things a little bit troublesome. But you see that the derivative of that is what you have outside. And that gives us an idea that you need to use substitution. Substitution. So you simply put u equals to your problem, so to say. You get the u dx equals to 2x. If you multiply with dx and then divide by 2x, you get this. So your integral would be this. So we keep the 2x, we substitute x squared plus 1 for u, and we substitute our dx for du over 2x, which is nice because then we can cancel the 2x's. And we have a very nice little integral, which is quite simple to find the integral of. And then we have our results. Substitute back to x squared plus 1, and we need to remember z, and that's it. You could check your result. You don't have to, but sometimes it's nice to do. Check. If you find the derivative of ex squared plus 1 and plus this integration constant, we need to use the chain rule again. X squared plus 1 times the derivative of the kernel here, which will be 2x. And the c will become 0. So if you compare this with that, you see that you have the same thing. This is not necessary, but useful. Okay. Sorry, my pen is clicking a bit. The last one. Here you see you have something with that is multiplied with something else by x. And the thing we have here now is quite simple to find the derivative and the integral of. So we will probably need to use integration by parts. So I put u equals to 3x and dv dx equals to ex. I take the derivative of that and I will get 3, and the integral of this and I get ex. So now I have 3x ex dx, which is now u times dv dx, because this u is 3x and this one is ex. So that will become u times v minus the integral of du dx times v dx. So that's my formula. So then I'll apply it. My u times v becomes 3x times ex minus the u dx is 3 and my v is ex. So 3x ex minus, I can put the 3 in front. The integral of ex is simply ex. And now I got rid of the last integration sign, so I need to add my integration constant. And here we have it. You could say, just on a side note, that why did I use integration by parts here and not in the last sub question? So just on a side note here. What makes 2x ex squared plus 1 dx different from 3x ex? Why do we use substitution here and integration by parts here? Well, the thing is that if we used integration by parts here, I get a very complex v. I cannot find the integration thing of that easily. So it doesn't really work. I could do it the other way around with u equals ex squared plus 1 and v dx equals to 2x. But then I'll get x squared here. And here I'll get, using the chain rule. So when I'm supposed to find the integral of this, right, you have uv minus thing. This one will be this, and this one will be that. So I'll have 2x to the third, which is really not simpler than with 2x. So this will just make it more complicated, so don't do that. Likewise, I cannot use substitution on this, because if I put u equals to x, I will not really get rid of this one. You can try that by yourself. But the main thing is that this will become 1, so the u will equal the x, so I will have 3x eu du, and I will still have the x here. So that's why I'm trying to see before I use substitution if the derivative of u is elsewhere in my integration as it is on this one. So integration by parts here, because I have something with x multiplied with something else by x, and it becomes simpler when I use integration by parts. And here, because this is making trouble for me, and the derivative of that is already in the integration.